we're going to talk a little bit about the common ion effect. I know I've probably mentioned already a couple of times in the context of laboratories, but really a common ion is any ion that is in the solution or can be presented in the solution that's in common with the ions produced by the reaction you're studying. So if you, for example, this is something we've already done in a lab, if you have 0.1 molar X in solution and you dissolve MX into the solution, then the common ion is X. And we'll talk more about the behaviors of that, but again, it's just the nomenclature. You have X from another source. And then there's another way the common ions present, and that's when you have another chemical equilibrium, and in that reaction, it also produces a concentration of an ion that's present in the equilibrium that you're trying to study. So in this case, the second reaction produces 2X ions as a result of some sort of equilibrium, and then that X ion is present in the reaction that you're studying. Okay, so again, different ways, but they all just basically mean that you're producing some of the same ions in a couple of different reactions, or you're producing an ion that's already present in the solution. Now, when you're talking about instances of this second case, oftentimes what you'll hear them called is coupled chemical reactions. And the reason they're called coupled chemical reactions is the Chatelier's principle basically ties them together at the point at which they intersect, that is, with a concentration of X. So imagine if these were two slightly soluble compounds. That's the context of the chapter we're dealing with now. But it doesn't have to be precipitation type reactions. But let's say you added some N2 to the solution, right? N2 plus, sorry, sounds like nitrogen. So we make this go up like that. What's going to happen? Well, the equilibrium is going to shift to the left, correct? Right? And that is, as a result, this is going to go down. And if this goes down, this presents in the other equilibrium as this has been changed, and then the equilibrium will shift to the right. And that is the sense in which they are coupled. You can make manipulations of an ion and indirectly affect another reaction based on the ion they're coupled together by. So before we sort of get into some of the details, I wanted to show you something that maybe would go unnoticed otherwise, and that is that if you look at the types of compounds that are formed in these solubility calculations, a lot of them are either hydroxides, like aluminum hydroxide here. Let's see, where else do we have another hydroxide? Cobalt hydroxide, copper hydroxide, iron hydroxide is on the next page, calcium hydroxide, cadmium hydroxide, and barium hydroxide. So you notice there's a lot of different hydroxides, and the other one that you often see are sulfides. So there's cadmium, let's see, where's the other ones? Calcium doesn't make one, cobalt sulfide, copper sulfide, there we go. And then notice for the sulfides, the solubilities are extremely low, right? And the hydroxides, there's lots of different examples. Another class that you see a lot of is carbonates, and carbonates and sulfides will essentially talk about together. But anyways, there's a lot of them, and these all have a common ion. The common ion for the hydroxides is hydroxide. So if you have hydroxide present in solution, it's a common ion, and it will affect the solubility. Sulfides and carbonates, that's what I meant to say before. We're going to talk about sulfides and carbonates together in a fashion. And sulfides and carbonates are tied together by the idea that those are the conjugate bases of weak acids, and I'll have a little section talking about that later. So just sort of get into the common ion effect in hydroxide. Let's look at a solubility product calculation with manganese hydroxide. Its KSP is 1.6 times 10 to the minus 13. And what we're going to do is calculate the solubility in pure water and look to see how that solubility compares when the manganese hydroxide dissolves in a solution with the hydroxide ion already present. So the common ions for this particular reaction will be the OH minus. Okay. And then if you had something with manganese, you could also set up the same kind of calculation to show that there's a common ion effect with the manganese just by starting with the manganese in the solution. So for example, if you had 0.010 molar Mn2 plus in solution, that would be another type of common ion effect. So we often focus on the hydroxide in these, but it's important to recognize manganese and the hydroxide could both be fall into the category of common ion effect. So let's go ahead and calculate the solubility in pure water. And to do that, we're just going to cheat a little bit. We're going to say KSP is going to be equal to S, because there's a 1 here, times 2S, because of 2 here, and this will be squared, so this is 4S cubed. And then what we'll do is we'll solve for S, and that gives me 3.42 times 10 to the minus fifth. Now, when you're going to do the molar solubility, right, in 0.01 molar hydroxide, you have to recognize that the KSP expression will have to contain this at the beginning. So we're going to have KSP is equal to S, because it's not that I'm adding manganese, I'm adding hydroxide, plus 0.010 plus 2S squared. Now, it's not a simple matter now of going ahead and saying, oh, well, yeah, I'm just going to plug it in and solve for S, because now this becomes a quadratic equation. Okay? Actually, it's a cubic equation, I guess it was what it really comes out to be. So you may have to pull out a solver, or you might be able to do an approximation, but let's go ahead and set this calculation up for the solver. So just for fun, I did actually set it up in my emulator. I'm going to go ahead and solve. Yeah, and so I get this 1.59999, so I'll call it 1.6 times 10 to the minus 9. All right. So that's S is equal to 1.6 times 10 to the minus 9 for my molar solubility when 0.1 molar hydroxide is present. And notice what happened to the magnitude of S. All right. I started out at 10 to the minus 5, and then I was able, this is how much dissolves in pure water, but if I have some hydroxide present in the solution, it's not very much, right? Then what ends up happening is the concentration that can dissolve is much, much smaller because of the presence of this small amount of hydroxide in the solution to begin with. Now, having said that, notice what happened here. I have 1.6 times 10 to the minus 9. This is 1.6 times 10 to the minus 13. It's not a coincidence that these two numbers are the same. And the reason they're the same is we can in this chapter, like we can in a lot of the subsequent calculations, use an X, or in this case S is small approximation. So let me go ahead and show you how you do that. You say KSP is equal to S times 0.010 plus 2S squared. And what we're doing is we're assuming that since that S is going to be small, because my solubility product is small. Now, it turns out this doesn't always work out because of the math. It is the exponents sometimes throw things off, and it's not always easy to predict. But when we go ahead and do that, then what we end up with is that KSP is equal to S times 0.010 squared. So that means S for this problem would be 1.6 times 10 to the minus 13, that's KSP, divided by 0.01 to the second power. Well, that's 4, right? 10 to the minus 4. So what's going to end up happening is this will be 1.6 times 10 to the minus 9, like that, because I'm dividing by 10 to the minus 4 down here. So the S is small approximation worked in the sense that this concentration for S is much smaller than 0.01. And again, I don't know if you remember me saying this in the previous chapter. It's sort of like the self-fulfilling prophecy. You run the calculation, and then you can tell that the approximation worked out because S is much smaller than the value you're comparing it to here. Okay, so this is another one of those things you just have to get used to. And that is the use of pH in these problems. And we often have to calculate the solubility of a substance at a particular pH. And when they say the solubility, what is the solubility of manganese hydroxide at pH 12, right? What you have to do is you just assume that this is the equilibrium concentration. So how did it get that way? Well, sometimes it's presented as a buffer problem, right? And when you have the buffer, it holds the concentration at a particular value. So in this example, right, we're going to go ahead and assume OH is the equilibrium value, and then this is where students will sometimes get stuck and not know what to do, but it's actually, this is the simplest problem that we can do, it turns out. We know that this is going to be the concentration of manganese and hydroxide squared, and again, it's equal to 1.6 times 10 to the minus 13. So if this is an equilibrium concentration, and this is the constant, this is the only thing that's unknown. So you can just rearrange the equation and say the concentration of manganese equals KSP over the concentration of hydroxide, because by default we're assuming it's the equilibrium concentration. So these calculations in like this one and this one are very similar and will give similar types of results. But if it says pH, then we're just assuming that it's being held at that constant concentration. So this is KSP. So this is going to be 1.6 times 10 to the minus 13. And then we just need to know what this value is, right? Well, if the pH is 2, right, then the POH is, if the pH is 12, I was thinking about the answer in my head, then the POH is 2.0, so the concentration of hydroxide is 10 to the, sometimes leave exponents off, 1 times 10 to the minus 2, right? And so I can just plug that value in there. Well, in fact, that's 0.010 squared, and I'll get 1.6 times 10 to the minus 9. So what was really weird about this problem, right? This is actually the same problem as this one, except the difference in the wording is that this one is present at the beginning, right? And this one is the equilibrium concentration because it's the pH. But because, right, the molar solubility is typically really small, these two numbers are, the numbers for this problem and for this problem are essentially the same. And so that's why we ended up getting the same answer for the concentration of manganese. Okay, so, and manganese, right, is S. It's the molar, it's related in the ice table. This would be S. That's the molar solubility of the compound.